Hello everyone, welcome back to another video from the Mathnasium. Today we are going to be talking about kind of some traits of sampling distributions, and we're going to hopefully be able to run through this. I'm going to try and go quick if I can, because some of it's recap from what we did last time, and then we're going to really see some things come full circle today. So I'm really excited to be on this statistical journey with you. So make sure strap yourselves in. I mean, this is going to be an emotional. This is going to be an emotional roller coaster, like Toy Story, probably. At least that level of emotional oscillating will be happening during this this lesson. Yeah, let's go ahead and jump right in. Let's first flash back to the googly eyes activity that we did. We're just going to remind ourselves what happened. You didn't know how many googly eyes I had, but I numbered them 1 up to n, some number, and then you had to guess what that number was. Now, before we actually did our guess, you guys tested. You came up with your own statistics. You did combinations of statistics. You doubled the median. You doubled the mean of your sample of 7 to try and get a guess at the total number. But you weren't doing it with the googly eyes. You were doing it with a set population that we knew the count of, and that count was 100. So just a quick refresher to last time. We had right here, we had our population distribution that we were doing on our calculators was generating a random number from 0 to 100. Each number had a 1 in 100 chance of being selected. So this was our population distribution that we were sampling from. And then we generated, each group generated 5 random samples without replacement from a population of size 100, and then you generated 7 numbers, but you did that 5 times. Okay, so each of those was the distribution of your sample, right? So you had 5 samples, each one had its own distribution, and then what we did is we calculated the 3 different statistics. And what each of these were we took our we took our 7 numbers, and then we used those numbers, and we used our 3 statistics to take a guess at the total. And each of our 5 samples of 7 numbers gave us a dot. So 1 dot represents calculating the statistic that we chose to guess at the total population from one of my 5 samples. And we were able to look in and look at basically say, well, which of these statistics did the best job of guessing at the true population mean of 100, which we knew, right? We knew that was the true population mean. And it looks to me, based on this would be NHAT1. Now, I just made up these data points. So what we're going to do today is we're going to talk about the language we use to describe, so each of these, this is the sampling distribution, or rather a very rough attempt at approximating the sampling distribution for NHAT3, NHAT2, and NHAT1. We're going to talk about how we compare these, the language that we use, and we're going to introduce a couple new vocabulary words. So let's get going. So just a quick reminder that we use statistics, right? We calculate statistics from samples, and we use those to estimate a parameter from a population. Now, since we're using statistics to estimate, and it's not always clear which one is the best one to use. Like, sometimes we have to do some sort of a study to figure out which one is the best to use. And so we sometimes call our statistics estimators. So estimators and statistics, we can kind of use those interchangeably if we're trying to take a guess at a population parameter. So your first vocabulary word is unbiased estimator. An unbiased estimator is a statistic where the mean of its sampling distribution is equal to the true population parameter. So let's take a look. Remember the, excuse me, I gotta take a quick drink. Hold on, pause game. Okay, I'm back. If we take a look at each of these, so this was one method, the other method, how do we determine which one was biased? Well, the ones that are biased are the ones that are not centered on the true population value, and that's what this is saying. So basically, we're looking this as just a couple 5 dots in a row. When we look at this in terms of a true, let's say we were trying to guess, like an actual population mean. Oh, that's too thin. Try that again. Sorry, I'm using a new program here. Let's say we were trying to actually guess a population mean here. Oh, come on, man. What is going on? Alright, well, let me just undo there. Boom, 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 boom. There we go. Color, got it selected. Here's our population mean that we are trying to guess. And let's say we go out and we decide on a particular statistic to use. If that statistic is unbiased, then we should see all of the dots for our, I'll make these nice and big here, all of the dots for our distribution. You should see a peak on your distribution, and that distribution should be somewhat centered on the true population value. So, but that's what we're seeing here, where it's like we're looking above the curve. We're seeing that this n hat 3 is centered on the true population value, and n hat 1 is centered on the true population value. So we would call n hat 1 and n hat 3 an unbiased. They are unbiased estimators of this is roughly speaking of the true population mean. Okay, but really you're supposed to look at the entire sampling distribution, not just 5 of the sample means, right? Or that's not enough. Okay, a biased one is going to have a curve that is consistently overestimating or consistently underestimating. Basically, not all, it doesn't have to be all the time, right? But if it is not centered on the true population value, in fact, we would call it biased even if it was just remotely off, right? If it was just even slightly off, like if the peak was right here and it came down this way, I would still call this biased because the center is not directly above the population mean. So an unbiased estimator consistently under approximates or over approximates. Okay, so you'll get basically an estimate that's always above or always below the true population parameter when you're making that guess. Okay, let's go back and head on to the next thing. And we've kind of seen this before. We talked about high accuracy and precision and the difference between those things. Well, the type of statistics we want, right? We want this type. But it's not always easy to decide. Sometimes the differences may be very slight, and so we have to really have a good justification for which statistic we're going to use. But it's really the same thing. When I was saying accurate prior in this class, and I gave this analogy, accuracy is where it is centered. That really just means its level of bias. Is the statistic centered on the population parameter? So this one is unbiased. This one looks like it's kind of unbiased. These two are biased. They're not centered on the bullseye, if that's where we are indeed aiming in this metaphor. So accuracy, where you are like where you are centered, can be said as just bias or unbiased, right? Being precise, precision is how tight the pattern is. So here we are not accurate because we're not centered on the bullseye, but we are very, very precise. This is probably the worst, right? We're never going to get our population parameter. If this is the parameter, we're way, way, way off. So we want one of these. We want to have low variability. We want it to be precise and accurate. We want low variability, and we want it to be unbiased. Basically, we want it centered on our population parameter. We want a really tight group so that every one of our guesses is going to be close to the thing that we want. Okay? So let's think about the 4 tall people from last time. So let's assume this is our entire population, and we want to understand 2 of the parameters from this population. The 2 parameters we're going to look at are, we are going to look at the population mean. We're trying to guess, we want to guess mu, the population mean. And we also want to guess, the population range. Now, we can calculate both of those, right now if we wanted to. They're very easy. The population range is equal to the maximum minus the minimum, which is 78 minus 73, which is equal to 5. So we can calculate what the population range is immediately. What's the population mean? Well, we would have to add these things up, which doesn't take too long, so we can do that pretty fast. That is 73 plus 78 plus 76 plus 74 divided by 4, which will give us what? Something. It'll give us a number. I'm going to pause for calculations. I think it's 75.25. Yeah, that's right. All right, so we can add those up and make that happen. We can find those. So this is what we're guessing at, right? And then last time I kind of did some math here, and I said, all right, here's our 4 tall people. Let's find the sampling distribution for x bar, the sample mean, with n equals 2. And so what we did is we found every single, so remember the true sampling distribution is every conceivable sample of that size. So we did every sample of size 2, and then, which are these 6 samples. We calculated all of their means. We made a little chart, which I believe is still on the 77, 76, 75, 74, 73, which I believe is still on the board there. So you have one at 75.5, which is right here. You have a dot at 74.5, which is right here. 73.5. You don't need to draw the graph again. 77, 76, and 75. So our population mean, which is like our balance point, here we know to be 75.25. Now I got that from getting all these together, adding them up, and dividing by 4 on the previous screen. Now, if you look here, if we do this math and we say, all right, well, this is every possible sample of size 2 and the means from those samples. What if we get the average of these things? That is to say, I'm going to have to write smaller. What if we did 75.5 plus 74.5 plus 73.5 plus 77 plus 76 plus 75. What if we added up all of these things and then divided by 6? So what this would be is this is the mean of this sampling distribution. This is the balance point of these 6 dots. Well, guess what we get? We get 75.25. And since the population mean is 75.25, that means that this technique, this statistic, that means that the sample mean x bar with n equal to 2 is an unbiased estimator of population mean. Mu, because they were the same. Now, did any of the values equal 75.25? No. Yeah, so, and it's not even the sample mean with x bar with n equals 2, it should be every sample mean. So every single sample mean basically is an unbiased. The mean is sample mean is an unbiased estimator of the population mean because they had the same. We took the sampling distribution, right? So we took the sampling distribution, the entire thing. We found the mean of that sampling distribution. They were the same, ergo, which means therefore sample mean is an unbiased estimator. I feel like I'm repeating myself. Maybe I am. Okay, so let's take a look at one that's biased. Let's take a look at the range. So in this case, this is also graphed on the board. You have a 1, a 2, a 3, a 4, 5, a 6, whatever. And then what does our distribution look like? It looks like this here is our sampling distribution. There's a 1, a 2, a 2, a 3, a 4, and a 5. That's all of them. A 1, a 2, a 2, a 3, a 4, and a 5. Okay. So this is the sampling distribution, this thing in green and these numbers in green, for the sample range with n equals 2. Let's calculate the mean of this sampling distribution. The mean of this sampling distribution is 1 plus 2 plus 3, I forgot the other 2, plus 4 plus 5. So add all those up and you get, we're going to divide by 6. What is the mean of all the ranges? So what is the mean of this distribution? It is, looks like 4, or 3, 6, 7, 8, 9, 10, 11, 12, 17 over 6, which is a number. 2.83. So the average, basically, the mean of the ranges of every sample of size 2 is 2.83. But here we see that the population range that we calculated earlier was actually 5. So when we take a look here, in this instance, the population range is right here. Here's the true range, the true parameter, the true population range. So what are we to get at here? Well, if you look at the curve, this curve, does it appear to you that this distribution is centered on the true population value? The answer, of course, here is no. The population range is equal to 5. So what's our conclusion? The sample range is a biased, biased estimator of population range. So this is no good. This is not a good method. And that's really obvious, right? Because when you take a small sample, you're not going to get all of the values. So might some of the samples have the true range? Yes, some of them will. But really only, the ones that have those two ending values. So you're not going to get it most of the time. So most of the time you're likely to be wrong. So this is not good. This is not a good thing, and you shouldn't do this. You shouldn't use the sample range to take a guess at the population range. Okay. Whew. Let's keep going. We're almost done. How are we doing on time? Look at that, 20 minutes. Okay. What if we did? What happens if we do this again, but we instead do this with a sample size of 3? So we have these 4 heights. What happens when we do this? Sample size of size 3. Okay, so range from, so we'll do like 74, 75, 76, like this. So clearly you can see this is every possible sample of size 3. These are all of those samples' means. So here is the sampling distribution. These purple numbers here is our sampling distribution for the sample mean with n equals 3. 75.7, we'll say that's right there. 75 is right here. 76 is right there. And 74.3 is right here. Okay, so where is this centered? Where is the center? The true population mean we already know. We know that it is 75. So mu equals 75.25. We already know that. If we increase the sample size, what did that do to the spread between those two? Well, here I was going from the lowest value was 73.5 up to 77. And here we went from 74.3 to 76. So here we're looking at how spread out the sampling distribution is, and it got much tighter. But if you do the math with sample size of 3, and this time we do 75.7 plus 75 plus 74.3 plus 76, and we divide that by 4, and we find what the mean of this sampling distribution is. Guess what it is? It's 75.25. So what's to be learned from this? When we increase the sample size, that is going to decrease the variability of the sampling distribution. Well, there's a no-brainer there. I wanted you to see it with the physical calculations. I know I've mentioned it before. When we increase sample size, comma, the variability of our statistic decreases. Beauty. And it still stays the same. So we can also say here, like, this is still sample mean. It's still centered. It's still unbiased. It just got tighter. So sample size of size 3 is the best statistic of the 3 that we looked at because it has lower variability. It's closer to the true value, and it has less variability. Boom. Centered. It's late. I'm sorry, I may have just repeated myself. I don't know what's happening. Move on. Okay, let's make a quick connection. I think this is going to kind of close us out here for the lesson. Yeah, I think we're good. I want us to think back just for a second when I introduced you guys to the sample standard deviation. Ignore this chart for just 1 second. The formula for the sample standard deviation is equal to, you take all the values and then you subtract the mean. I don't know if you remember this. Then you square it. then you divide by n minus 1. And what this is supposed to do, the interpretation of the standard deviation, it is in our data set, how far away from the mean did the typical value fall? And a lot of people were saying, well, if it's like the typical value, that sounds like the average. Why are we dividing by n minus 1? And I said, guys, I'm going to explain this to you later. I think I said something along those lines. We're going to talk about this later. You also know that S sub x is, so this one is the variance if we square it, right? So the square root of the variance is equal to the standard deviation. So what I have here down below is, let's pretend, people were trying to, you're trying to get there's this thing called the standard deviation, you didn't know what it was, and people are trying to come up with the right way to talk about the spread. Okay, and so people proposed two different statistics to get the population standard deviation, or the population variance. In this case, remember, we would just get rid of the square root here. And so in the top example here, they divided by n minus 1. In the bottom example, this is a biased estimator. So this one is biased. In this example, this one is unbiased. In this example, they took a population, I think it was like 500 individuals, and they knew the population variance was equal to 9. And then they took a ton of samples, and then from those samples, in each sample, they calculated, so this one was the sample variance. This was the sample variance using n minus 1. This one down here was the sample variance using just n. When I say using, I mean dividing right here. Now, you can see, so what they did here is they resampled from a population with a known variance. They knew what the population variance was. And when they did this with a computer a bunch of times, they found that when you use n minus 1, it ends up being unbiased because the true parameter of interest, which is the variance of our population, ended up being the approximate mean of our sampling distribution for all the variances calculated. So each of these dots represents the sample variance from a sample that they pulled from this big population that had variance 9. And when you took the mean of all of them, when you used n minus 1, it was lined up right on where it was supposed to. If you didn't, if you divided by n, then x bar, so here we're using n, right? So we put n here instead. If you divide by n, you end up getting an x bar that is an under approximation when we know that the true population value, the true variance is here, which means that dividing by n in this situation is biased. Okay, and that's kind of a long explanation you probably didn't need to hear. Hopefully this cleared up some things for you guys. I had some fun looking through and researching this. I should be back soon, and the assignments posted online as well as the solutions. We'll see you soon.